Now in the previous session, now I am saying that now there are different types of inputs and different types of responses. Therefore, now we will see the relation between one response is converted to another response and one input is converted to another input, we will see. Then now see here, this is parabolic response. Okay. Then you are applying a parabolic input, then you can get the parabolic response. Then if you differentiate this parabolic response, what is the differentiation of parabolic? Which means that the parabolic is nothing but a by 2 into t square. If you differentiate a by 2 into t square means 2t, 2 to cancel, which is equal to at. Which means if you differentiate parabolic, which is nothing but ramp. Therefore, if you differentiate the parabolic response, then you can get the ramp response. So, if you differentiate the parabolic response, then that resultant response is nothing but the ramp response. Now, in the same manner, then if I differentiate ramp response, if I differentiate the ramp response, then the ramp is nothing but a into t. Differentiation is a, t means 1. Now what is a? Which is constant, is nothing but the step. Therefore, if you differentiate the ramp response, this is nothing but step response. Now, similarly, now if you differentiate the step response, then step is nothing but a constant. Differentiation of constant is nothing but 0. At 0, which signal is existing? At origin only one signal is existing, that is nothing but the impulse. Therefore, the differentiation of step response is nothing but the impulse response. The differentiation of step response is nothing but the impulse response. Now these are the conversion from one response to another response. Then from here we have another relation. Now see here, if we want the ramp response is available for us, but I want parabolic response, then what should you do? Then we have a ramp response, then we want to find the parabolic response. Therefore, if you integrate, then you can get the parabolic response or not. Therefore, if you integrate the ramp response, then you can get the parabolic response. If you integrate the ramp response, then you can get the parabolic response. Now, if you integrate the step response, then we can get the ramp response. If you integrate the step response, then we can get the ramp response. Now in the same manner, if I integrate the impulse response, if I integrate the impulse response then you can get the step response. But all the signals what we consider only for the positive signals, because when it is in the frequency domain, therefore it is only a positive frequencies are existing practically. Therefore you consider these are the positive signals, therefore integrating for all the positive values of time. Integrate for all the positive values of time. If you integrate for all the positive values of time, then you can get the different responses. But here these are the responses on converting from one response to another response. But here we want to consider one note here. One note you have to be considered. This is also important. What is that note? All these relations you used only for converting from one response to another response. But for finding the transfer function, use the standard formula only. All these relations are used for converting from one response to another response. But for finding transfer function, use the standard formula, which is Laplace transformation of output to the Laplace transformation of input with all initial conditions are equal to 0. Now these are the relations for converting from one response to another response, and for finding the one response to another response, use these relations. Then if you want to find the transfer function, then use this standard formula, which is Laplace transformation of output to the Laplace transformation of input with all initial conditions are equal to 0. Note down this. Right. Now, generally we are taking any control system now whose basic behavior is generally a behavior of the resistor, inductor or capacitor. Now you are already have a familiar with of the resistor, inductor, capacitor behavior. Just we go through a small portion of that particular element, such that which is useful for our further analysis. Then what I am doing here is I just take a capacitor here, capacitor. Now this is a parallel plate capacitor. This is a parallel plate capacitor. Now this is a parallel plate capacitor. Then if you see here, if I apply a voltage across this capacitor, then this capacitor starts charging. Like your cell phone battery. Then you just plug in the charger, then it starts charging. Now similarly here is also. Now the amount of charge, what is the amount of charge? The amount of charge stored in this capacitor is directly proportional to applied voltage. The amount of charge stored in the capacitor is directly proportional to applied voltage. If I remove this proportionality, would you put a constant? Now that proportionality constant or a linear constant or a slope, which is nothing but C. Therefore, now see here, with respect to charge versus applied voltage. Now, with respect to charge versus applied voltage, then if I take a curve with respect to charge versus applied voltage, the characteristics are linear and this is linearly varying, and this proportionality constant or slope is C. Now, see here, this is a charge versus applied voltage. The characteristics are linear and the linear constant or proportionality constant or slope is C. Now see here, now what is the current? The current, which is nothing but rate of change of charge. Now what is the current? The current, which is nothing but the rate of change of charge. Now what is the current passing through the capacitor, which is nothing but rate of change of charge. What is the charge? Charge is nothing but C into V. Therefore, the current passing through the capacitor IC, which is equal to IC, which is equal to C into dV by dt. Now this is the current passing through the capacitor, which is equal to now d by dt into C. C is constant, C into dV by dt. Then from here, then what is the voltage? Can I write like this? Voltage, which is equal to 1 by C integral I into dt. Therefore, if I take this is with respect to time, so V of t, which is equal to 1 by C integral I of t into dt. This is voltage across the capacitor. Now this is current passing through the capacitor. Then if I want to see its behavior in time domain, then if you apply the Laplace transformation, then apply Laplace transformation. What is the Laplace transformation of V of t? The Laplace transformation of V of t is V of s, which is equal to 1 by C into Laplace transformation of integration is 1 by s into I of s. Therefore, now see here, therefore now V of s by I of s, V of s by I of s, which is equal to 1 by sc. Now V by I is nothing but the resistance. Now the resistance offered by this capacitor, which is nothing but capacitive reactance. Now this is the V by I is the resistance. The resistance offered by this capacitor is nothing but the capacitive reactance, which is nothing but 1 by sc. Now let us assume what is s? S equal to sigma plus j omega. If you assume real part equal 0, s equal to j omega. If I assume real part equal to 0, if I assume sigma equal to 0, now s equal to j omega, which is nothing but 1 divided by j omega into C. Now this is the resistance offered by capacitor, which is nothing but capacitive reactance. Units are ohms. This is the resistance offered by capacitor, which is nothing but a capacitive reactance. Units are ohms. Now from here we can easily identify. Now this is a capacitor in time domain. This is C in time domain. If we apply Laplace transformation, the Laplace transformation of C, which is nothing but the Laplace transformation of C, which is nothing but 1 by sc. Now the Laplace transformation of C, which is nothing but 1 by sc, because we slowly converted the total analysis into frequency domain. Therefore, there we required all these particular values, and this is the behavior of the capacitor. Now finally we conclude that now with respect to charge versus applied voltage, with respect to charge versus charge versus applied voltage, now the capacitor is said to be linear and time invariant. Now with respect to charge versus applied voltage, the characteristics are linear and which is passing through the origin, because these are linear characteristics. Now with respect to charge versus applied voltage, the capacitor is said to be linear and time invariant, and this is the behavior of the capacitor. Okay, you just take this one. Then after that we will see the remaining two elements, which is inductor and resistor. Now these three elements which are continuously useful and throughout the behavior of any control system. Right, now we will see the another element, which is nothing but inductor coil. Then now if you take a coil, now then if you apply a voltage across this coil, then you see here, now this is a coil, if you take the voltage across this coil, now this is a coil, if you take a voltage across this coil, then this current is passing through this coil. Then if you see here, now where is my thumb? Now this thumb indicates the direction of the current flowing, and these fingers are folding in this direction. Now in this particular direction, the flux will be linkage. Now in this direction, the magnetic flux is linkage, and through the thumb direction, the current is passing through the coil. Now what happened now? Now this is the current passing through this coil, and this is the flux linkage. Now in this direction, the magnetic flux is linkage. Therefore, the amount of magnetic flux linkage through this coil is directly proportional to the current passing through the coil. If you remove this proportionality, we put a constant. Therefore, then this proportionality constant is nothing but L, phi equal to L into I. Therefore, this is flux versus current passing through the coil. Therefore, now if you see here, now if you draw the characteristics, now this is the amount of magnetic flux and this is the current passing through the coil. So the magnetic flux is passing through the coil is directly proportional to amount of current passing through the coil. Then these characteristics are linear, and this linearity constant or the proportionality constant, which is nothing but L. The amount of magnetic flux is proportional to the current passing through the coil. Then if you remove the proportionality, put a constant, that is nothing but the inductance L. So now in the same way here also, this is the linear characteristics. So the voltage which is equal to rate of change of this flux, then this is nothing but the rate of change of what is this flux? Flux equal to L into I. Therefore this L is constant, so V equal to L into di by dt. Therefore now V of t, which is equal to L into di by dt. If I take in time domain, now this is voltage across the coil, this is current passing through the coil. Then if I apply the Laplace transformation, now V of t, which is equal to V of s equal to L, Laplace transformation of derivative is s into I of s. Therefore if I see here, V of s by I of s, V of s by I of s, which is equal to L into s, which is equal to, if I replace s equal to j omega, therefore this is j omega L. The resistance offered by inductor, which is nothing but inductive reactance, which is equal to ohms. Therefore this is inductive reactance represented by XL. The voltage, voltage across the inductor. So VL of S by VA of S by I of S. Now the resistance offered by inductor, inductive reactance, then the units are ohms. Then let us assume the real part equal to 0. Therefore then from here also we can say that the Laplace transformation of the inductor L, the Laplace transformation of inductor L, which is nothing but in frequency domain Ls, Laplace transformation of L, which is equal to Ls. Now with respect to flux versus current, now the inductor is said to be linear. This is the linear characteristics and time invariant. With respect to flux versus current, the inductor is said to be linear and time invariant. This is another element which is nothing but the inductor. Then we will see one more element, that is resistor, which we will see. Now first you take this one. Now resistor R. Now this is the voltage across this element and the current is passing through this element. Now the voltage across this voltage drop across this element, the voltage drop across this element is directly proportional to current passing through this element. The voltage drop across this element is directly proportional to current passing through this element. Therefore, if I remove this proportionality constant, then that proportionality constant or slope is nothing but R. The drop across this element is directly proportional to current passing through this element. Therefore, if I draw the characteristics of voltage drop across this element and current passing through this is the voltage drop across this element and this is current passing through this element, that the characteristics are linear because this is directly proportional. The characteristics are linear and this linearity constant or a slope is R. And we know that the behavior of the resistor, which is always dissipative in nature, which is always opposes the flow of current. Now, with respect to voltage drop versus current, the resistor is always linear and time invariant. With respect to voltage drop versus current, the element resistor is always linear and time invariant, and resistor is always dissipative in nature, which is always opposes the flow of current. Therefore, the behavior of the resistor, whether it is in time domain or frequency domain, will be same. Therefore, the resistor is always dissipative in nature. Now, whose basic behavior, which is always opposes the flow of current. Therefore, the behavior of the resistor, whether it is in a time domain or frequency domain, both are same. Therefore, the Laplace transformation of R, which is nothing but R only. Now, these are the three elements now, which is nothing but the resistor, inductor, capacitor. And if you observe all these three elements with respect to two parameters, voltage versus current, or flux versus current, or charge versus voltage, the characteristics are linear and time invariant. If you observe, all the three elements are linear and time invariant with respect to the parameters. right? Now we just have these three elements, just have a common properties. Now see here. Now this is the capacitor C in time domain. Now the Laplace transformation of capacitor C, which is nothing but 1 by SC, and the amount of energy stored in the capacitor is, which is stored, half CV square. This is the energy stored in the capacitor. So the amount of energy stored in the capacitor is always depends upon the applied voltage. Now this capacitor stores energy. This capacitor stores energy, and now in the same manner the Laplace transformation of inductor L, the Laplace transformation of inductor L, which is nothing but Ls. Now the energy stored in the inductor, which is nothing but half L I square joules. Now the energy stored in the inductor, which is nothing but, it depends upon current passing through the inductor, because here is a charge, here is the flux. So yes, it stores magnetic energy. Now the Laplace transformation of resistor R, which is nothing but R only. The energy stored in the inductor, no, the energy stored in the resistor does not store any energy, because which is always dissipative in nature. It does not store any energy, which is always dissipative in nature. The behavior of the resistor, whether it is in time domain or sequence domain, will be same. But all these three elements, the resistor, inductor, capacitor, all these three elements are having a common property, which is nothing but, now the inductor, resistor, inductor, capacitor are said to be linear and time invariant. Now the resistor, inductor, capacitor are said to be linear and time invariant. Therefore, with respect to flux versus current, with respect to charge versus applied voltage, with respect to voltage drop versus current, now all these elements are said to be linear and time invariant. Therefore, why I am saying like this, because any control system you take, whether it is an open loop control system or a closed loop control system, whose basic behavior is the behavior of resistor, inductor, capacitor, or a combination of these three, but these three elements are said to be linear time invariant, right? Therefore, that is the reason why the transfer function definition is also, we are defining for a linear time invariant system. You may be observed or not, in the first session we will see the transfer function definition. Now that transfer function definition, what we are doing is transfer function of a linear time invariant system. Why we mention the transfer function of a linear time invariant system? Means transfer function of a control system. Now any control system whose basic behavior is the behavior of resistor, inductor, capacitor, or a combination of these three, but these three elements are said to be linear time invariant. Therefore, the transfer function definition is valid for a linear time invariant system. Take this. Now we'll take one small example. Now this is the control system. This is output. This is input. This is output and this is input. That's what I'm saying. Any control system you take, that control system which is a combination of resistor, inductor, capacitor, or any of these three combinations. Then if you take any control system whose basic behavior is the behavior of resistor, inductor, capacitor, or a combination of these three elements. But what we know that just now we identified, but all these three elements are said to be, all these three elements are said to be linear time invariant. Therefore, can I say like that? Now any control system which is a combination of resistor, inductor, and whose basic behavior depends upon the resistor, capacitor, inductor behavior, but these three elements are said to be linear time invariant. So can I say like that? Therefore, the control system is said to be a linear time invariant system. Therefore, the control system is nothing but therefore we can say like this, therefore the control system is said to be linear time invariant system. That is the reason why therefore the transfer function definition is valid for the transfer function definition therefore the transfer function definition is valid for a linear time invariant system. Because any control system whose basic behavior is the behavior of resistor, inductor, capacitor, but these three elements are said to be linear time invariant. Therefore, my control system is said to be a linear time invariant system. Therefore, the transfer function definition and the transfer function analysis is valid for a linear time invariant system. The transfer function definition or transfer function, we can say the transfer function analysis, or the transfer function definition, which we already defined for a linear time invariant system. For a linear time invariant system, the transfer function definition is nothing but Laplace transformation of output by the Laplace transformation of input. Therefore, this transfer function analysis for a linear time invariant system, because my linear time invariant system is nothing but a control system, because any control system whose basic behavior is nothing but the behavior of resistor, inductor, capacitor, or a combination of these three. That is the reason why the transfer function is defined for a linear time invariant system. For a linear time invariant system, the transfer function is defined as a Laplace transformation of output to the Laplace transformation of input with all initial conditions are equal to 0. Take this. Now, from this, we have to find one important relation. Now, this is the control system. Now, is nothing but the control system. Now, this is nothing but a linear time invariant system. Linear time invariant system. Now, this is output, this is input, this is output, this is input. Now, this is a linear time invariant system. Linear time invariant system. Now, for a linear time invariant system, now see here, the transfer function which is equal to, now for a linear time invariant system, you know the definition of transfer function. What is the transfer function? The transfer function which is equal to Laplace transformation of output to the Laplace transformation of input with all initial conditions are equal to 0. This is the transfer function of a linear time invariant system. Therefore, now what I am doing here is, now this is the input, now I am applying an impulse input. Then if you apply the impulse input, then this response is nothing but the impulse response. Now I am applying an impulse input and this response is nothing but the impulse response. Therefore, for a linear time invariant system, what is the definition? The transfer function which is nothing but Laplace transformation of output. What is output? Output is nothing but impulse response. Now, Laplace transformation of input. What is input? The input which is nothing but the impulse input with all initial conditions are equal to 0. Therefore, now the Laplace transformation of impulse. What is the Laplace transformation of impulse? Which is equal to 1. Therefore, the transfer function definition is nothing but the transfer function of a linear time invariant system is nothing but directly the Laplace transformation of impulse, the Laplace transformation of impulse response with all initial conditions are equal to 0. This is one important definition of transfer function if there is a impulse response. Now in the questions or in our subject, sometimes you will get the impulse response. Where you can get the impulse response directly, you don't do anything, just simply apply the Laplace transformation of that impulse response. Now with all initial conditions are equal to 0 is nothing but the transfer function. This is the transfer function definition which you are getting from the standard definition of the transfer function. Output by input. Output is impulse response because you are giving the input as a impulse input. Therefore Laplace transformation of impulse which is equal to 1. Therefore this value will become now the Laplace transformation of impulse. Therefore this value which is equal to 1. Therefore Laplace transformation of impulse response with all initial conditions equal to 0 for a linear time invariant system is the definition of a transfer function. There are two definitions of the transfer function. Now this is the standard definition. The standard definition which is nothing but, this is the standard definition which is the transfer function of a linear time invariant system is defined as Laplace transformation of output to the Laplace transformation of input with all initial conditions are equal to 0. From that particular standard definition for a linear time invariant system, then we can have another definition for a linear time invariant system. The Laplace transformation of impulse response with all initial conditions are equal to 0 is nothing but the transfer function. Therefore, the another definition of the transfer function, the transfer function of a linear time invariant system is defined as Laplace transformation of impulse response with all initial conditions are equal to 0. So, this is the linear time invariant system. We have these two transfer functions which are very important for further analysis of the control system. Take this one. Now, based on that, we'll solve one question in our handbook. Now, in our workbook, question number 7. Question number 7. What is the question number 7? Now, based on this concept only, the impulse response of the control system is given as minus t into e power minus t plus 2 into e power minus t. This is given. The impulse response of the linear time invariant system is minus t into e power minus t plus 2 into e power minus t. Now what he is asking is find type and order. See how this is linked. Now he is giving the impulse response of the linear time invariant system. Now minus t into e power minus t plus 2 into e power minus t, and he is asking to find type and order. So we want to find the type and order. First we need to find the transfer function. So but how to find the transfer function? There are two formulas here. Laplace transformation of output to the Laplace transformation of input with all initial conditions are equal to 0. Just now we have another formula. Now if it is the impulse response is given for a linear time invariant system, the Laplace transformation of impulse response with all initial conditions are equal to 0 is nothing but the transfer function. Now use this concept and first you find the transfer function. Okay. Now this question which we solved in the next session.